Alpha Centauri is the closest star system to our own, only about 4.3 light-years away. That sounds near until the distance becomes a journey. Light crosses it in just over 4 years, but a spacecraft moving at Voyager-like speed would need tens of thousands. Long before arrival, Earth would fade into an ordinary star. Communication would take years, and every repair, illness, and human decision would have to be faced without help. Beyond the planets, the ship would enter an ocean of darkness where even a grain of dust could become dangerous, while the people who began the voyage might be gone generations before 3 distant suns appeared ahead. So tonight, the question is simple. What would it truly take to carry human life to Alpha Centauri? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If reaching Alpha Centauri meant leaving Earth forever, would you still volunteer? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about the terrifying journey to Alpha Centauri. Alpha Centauri is often described as the closest star system to our own, and the word closest makes it sound almost reachable. On a map of the galaxy, the distance between the Sun and Alpha Centauri is barely visible. Both systems belong to the same quiet region of the Milky Way, surrounded by stars that appear far more distant. From that perspective, Alpha Centauri seems like the natural place for humanity to travel, after learning how to move beyond the planets. But a galactic map hides almost everything that matters, because Alpha Centauri lies about 4.3 light-years away. Light, moving faster than anything with mass can travel, needs more than 4 years to cross the gap. The number sounds small only because the unit is enormous. 1 light-year is the distance light covers during an entire year, and light can circle Earth more than 7 times in a single second. Across 4.3 years, that distance becomes roughly 40 trillion kilometers. Written as a number, it is difficult to feel. The mind can read it, but there is nothing in ordinary life large enough to compare with it. Roads, oceans, and continents disappear inside the first tiny fraction. Even the distances between planets become small. The moon is far enough away that astronauts required several days to reach it. Alpha Centauri is more than 100 million times farther. The outer planets do little to close the gap. Voyager 1 has traveled farther from Earth than any other human-made object. It crossed the heliopause and entered interstellar space after decades of flight. Its signal now takes many hours to reach Earth, and the spacecraft is so distant that the Sun would appear much smaller from its location. Yet Voyager has covered only a tiny beginning of the distance to another star. At its present speed of roughly 17 kilometers per second relative to the Sun, a journey across the distance to Alpha Centauri would take around 75,000 years. The probe is not actually heading there, but the calculation reveals the scale. 75,000 years is longer than the entire history of cities, writing, agriculture, and every modern nation. A spacecraft launched at that speed, when early humans were moving through the last ice age, would still be traveling now, and the destination would remain ahead. Even our fastest probes do not make interstellar space feel small. They only show how slowly human machines move when the distance is measured between stars. The solar system itself is larger than the familiar arrangement of planets shown in diagrams. Beyond Neptune lie countless icy objects, and beyond them, the Sun's influence continues through a vast region of particles, magnetic fields, and distant bodies. Voyager needed 35 years merely to cross the heliopause, the boundary where the solar wind gives way to the interstellar environment. Alpha Centauri begins far beyond that boundary, so leaving the solar system would not mean that most of the journey was complete. It would mean the real emptiness had only started. This separation explains why the night sky changes so slowly. The stars appear close together because distance has been flattened into a view. Two points of light may look almost side by side, while one is hundreds of times farther away than the other. Alpha Centauri appears as one of the brighter objects in the southern sky, but nothing in its brightness reveals the empty volume between it and Earth. There are no roads connecting the systems, no stations placed along the route, and no planet waiting halfway with fuel, shelter, or spare parts. A spacecraft leaving the Sun would move through a region where every useful resource had to be carried from the beginning or created on board. If something essential were forgotten, there would be nowhere to obtain it later. The distance would also change communication. A radio message travels at the speed of light. Near the Moon, the delay is only a little more than 1 second each way. Near Mars, communication can take several minutes. At Alpha Centauri, one message would need more than 4 years to reach Earth, and a reply would need another 4 years to return. Even if a crew arrived safely, a simple exchange with home would take nearly a decade. Questions could not be answered in time to solve emergencies. Instructions would describe problems that had already changed, and the people sending the response might be speaking to a different generation from the one that asked. The distance creates independence before arrival. Long before the spacecraft reached Alpha Centauri, Earth would no longer function as a control room. It would become a source of delayed information, memory, and advice from the past. The outward journey would make this separation gradual. At first, Earth would remain a visible world behind the ship. Continents and clouds could still be seen. Then the planet would shrink into a bright point near the Sun. The Moon would vanish into the same distant glow. The spacecraft would pass Mars, the asteroid belt, and the giant planets. Each crossing would feel like progress because the planets provide landmarks, but beyond Neptune, those landmarks would end. The Sun would remain the brightest object behind the ship, but it would slowly lose its familiar appearance. Its warmth would weaken. Its light would become concentrated into a single star. This lack of visible motion could make the journey feel endless. On Earth, speed can be understood because nearby objects rush past. Trees, buildings, and clouds provide a sense of movement. In interstellar space, there would be almost nothing close enough to produce that effect. The spacecraft might travel millions of kilometers during a day, while the stars appeared unchanged. Alpha Centauri itself would remain a point for most of the crossing, growing brighter slowly, but not become a visible place with shape and depth until very late. The crew could spend years or generations traveling toward a destination that still looked like nothing more than light. The journey would therefore be measured less by scenery than by time, and days inside the spacecraft would be created by clocks and lighting, rather than sunrise. Months would be counted through maintenance schedules, food production, health checks, and repeated observations of systems that could not be allowed to fail, while outside the distance reduced by an amount too small to feel. The people who began the voyage might leave Earth knowing that they would never see Alpha Centauri. If the mission relied on a generation ship, their role would be to begin a journey completed by descendants who had never stood beneath an open sky. The people who arrived might know Earth only through recordings. Its oceans would be images. Rain would be sound stored in an archive. The smell of soil, the pressure of natural wind, and the sight of a horizon beneath one's sun could become experiences described by ancestors. The nearest star system would not merely be far away in space. It would be separated from Earth by human lifetimes. And even a much faster spacecraft would face this problem. Suppose a future ship could travel at 1% of the speed of light, far faster than any large vehicle built today. The crossing would still require more than 4 centuries, without including the time needed to accelerate and slow down. At 10% of light speed, the journey could be reduced to several decades. That begins to fit within a human lifetime, but the energy required becomes extraordinary. A massive crewed spacecraft would have to be accelerated to tens of thousands of kilometers per second. Later, it would need to lose nearly all of that speed before passing through the destination system. Moving fast enough to make the distance survivable creates new dangers, because interstellar gas and dust that seem nearly absent at low speed become serious threats. Navigation errors grow across trillions of kilometers. Shielding adds mass, and mass requires more energy. Every system must function long enough to complete a mission that no rescue craft could reach. The distance cannot be solved only by building a faster engine, because speed changes the nature of the journey. A slow ship needs to support many generations. A fast ship needs to survive enormous energy, radiation, heat, and impacts. A ship, somewhere between those extremes, may still be too slow for one lifetime and too demanding for technology that exists today. There is no comfortable speed waiting to be chosen, and the destination itself adds another uncertainty. Alpha Centauri is not one star. It is a system of three: Alpha Centauri A and B, two sun-like stars orbiting one another, and Proxima Centauri, a smaller red dwarf much farther from the bright pair. From Earth, the system can be spoken of as one destination because all three belong to the same nearby stellar neighborhood. From the perspective of an arriving spacecraft, their separation would matter, and the mission would need a specific target. It could travel toward Proxima, the closest individual star and the host of at least one known planet. It could aim for the brighter pair, where possible worlds would experience a very different environment. Choosing incorrectly could add more distance at the end of a journey that had already crossed 4 light-years. The word arrival becomes less simple when the destination is a moving system rather than a fixed point. The stars orbit, their planets move, and the spacecraft must meet them at a position predicted years or decades earlier. It cannot aim at where Alpha Centauri appears in the sky when the mission begins. That light already shows the system as it was, more than 4 years in the past, so the ship must travel toward where the target will be. A tiny error in direction repeated across 40 trillion kilometers could become an enormous miss. Course corrections would be possible, but each one would use energy that had to be carried or generated. The geometry of the journey would need to be planned with a precision unlike any voyage on Earth. Still, distance alone does not make Alpha Centauri impossible. Physics does not forbid a spacecraft from crossing the gap. A probe moving fast enough could reach the system. A human vessel with sufficient energy, protection, and reliability could also make the journey in principle. The difficulty lies in everything hidden inside the phrase sufficient. The ship would need the energy to accelerate, the shielding to survive, and enough food, air, water, living space, and repair capability to function for decades or centuries. It would also need precise navigation and a way to slow down at the destination. Every solution increases the size and complexity of the vessel, and a larger vessel requires still more energy. This is why Alpha Centauri feels both close and unreachable. It is close enough for its stars to be studied in detail. Their light reaches telescopes on Earth after only a few years, allowing astronomers to examine their motion, temperature, radiation, and possible planets. Yet direct travel changes a short delay in light into a physical crossing that must carry mass through the entire distance. Information can arrive from Alpha Centauri with no engine, no life support, and no shield, but a spacecraft cannot. The nearest neighboring system therefore marks a boundary between what humanity can observe and what it can reach. We can study its light tonight, detect the movement of its stars, and search for worlds around them. But sending even a small probe there, within a human lifetime, would require technology far beyond the machines now leaving the solar system. Sending people would require something larger than a vehicle, a protected, moving world. The distance itself decides this. A capsule cannot hold enough supplies for centuries. An ordinary station cannot accelerate to a meaningful fraction of light speed. A fragile probe cannot support human life, and a heavy habitat cannot be moved easily across interstellar space. The journey demands that propulsion, shelter, ecosystem, repair shop, hospital, power station, and home become one machine. Before anyone could face the darkness between the stars, humanity would first have to build an object capable of carrying a small piece of Earth farther than any living world had ever traveled. And once the true distance to the nearest star system had turned a seemingly short journey into a voyage across 40 trillion kilometers of empty space. The question was no longer simply how long it would take, but what kind of spacecraft could possibly remain alive for the entire crossing. The rockets that lift spacecraft from Earth are powerful because they must escape the lower atmosphere and gain orbital speed in only a few minutes. They burn enormous amounts of propellant, produce intense thrust, and then fall silent once their work is complete. This method is effective for reaching orbit and sending machines towards the planets. But the distance to Alpha Centauri changes the meaning of speed. A chemical rocket can give a spacecraft one great push. It cannot continue accelerating for years without carrying an impossible amount of fuel. Propellant has mass, and that mass must be accelerated along with the ship. Adding more fuel allows a longer burn, yet the extra fuel demands still more fuel to move it. The vehicle grows heavier, the tanks become larger, and the engine must work harder before the spacecraft has traveled a single kilometer toward another star. The fastest probes now leaving the solar system were not built for Alpha Centauri. They received powerful launches and carefully planned encounters with planets, then continued outward on momentum. Their speed is astonishing by the standards of human travel, but the space between stars is large enough to make that speed feel almost motionless. It would outlive nations, languages, and every institution that launched it. The machines inside would have to survive longer than recorded history, while generation after generation lived and died before the destination became meaningfully closer. Reducing that journey to centuries would require a spacecraft moving far faster than anything carrying people has ever moved. Reducing it to decades would demand a significant fraction of the speed of light. At 10% of light speed, Alpha Centauri would still be more than 40 years away before allowing time to accelerate and slow down. At 1%, the crossing would last more than 4 centuries. The ship must therefore do something no existing human vehicle can do: reach an extraordinary speed, protect itself while traveling at that speed, and preserve enough energy to stop when the destination finally arrives. A faster ship completes the voyage sooner, reducing the amount of food, replacement equipment, and living space needed across generations. But higher speed demands far more energy and makes collisions with dust more destructive. A heavier ship can carry thicker shielding, larger habitats, more spare parts, and a more stable population. Yet every added kilogram requires additional energy during acceleration and deceleration. It needs pressure vessels, water, air systems, medical equipment, food production, power, heat control, workshops, computers, shielding, and room for people to live without slowly damaging their bodies and minds. The spacecraft would be less like a rocket and more like a sealed world with an engine attached. Chemical propulsion might still be useful near Earth, carrying pieces into orbit where the interstellar vessel could be assembled. A ship large enough for a long human voyage may never stand on a launch pad as one complete object. Its structure could be built above the atmosphere from modules sent upward over many years. Even then, ordinary chemical engines would probably serve only the opening stages. They could move the ship away from Earth or help with smaller corrections. But the main acceleration would need a source of energy far beyond the rockets used today. Nuclear propulsion offers one path forward, though not yet one fast enough for a comfortable journey to Alpha Centauri. A nuclear thermal engine uses a reactor to heat a propellant and force the hot gas through a nozzle. It can use propellant more efficiently than a chemical rocket, while still producing meaningful thrust. Such an engine could shorten journeys within the solar system, and carry larger payloads toward distant planets. A nuclear thermal system would still need vast amounts of propellant for a heavy interstellar ship, and it would not naturally reach a large fraction of light speed. Nuclear electric propulsion uses a reactor differently. Instead of heating propellant directly, the reactor generates electricity, and that electricity accelerates charged particles through an engine. The thrust can be extremely gentle, yet it can continue for long periods while using propellant efficiently. A spacecraft might accelerate for months or years, gradually building a speed that a short chemical burn could never provide. A force too small to notice at one moment can transform the motion of a spacecraft when it continues without pause. The problem is the scale of the final speed required. Existing electric propulsion is useful for moving robotic spacecraft through the solar system, but a crewed interstellar vessel would need power systems far larger than anything yet flown. The reactor would have to operate reliably for decades. Its waste heat would have to escape through enormous radiators, because space is cold, but removing heat in vacuum is difficult. There is no air outside to carry warmth away. Energy must be released as radiation from large surfaces. And the more powerful the engine becomes, the more heat the ship must manage. A reactor failure far from the sun would not merely stop the engines. It could remove the electricity needed for life support, farming, communication, navigation, and protection. Fusion reactions release energy by joining light atomic nuclei, the same broad process that powers stars. In principle, fusion fuel could contain far more usable energy than chemical propellant, allowing an engine to push material from the rear of the ship at tremendous speed. A fusion-powered spacecraft might accelerate for years, coast across much of the distance, then turn and use its engines to slow before reaching Alpha Centauri. Humanity has not yet built a compact fusion power system capable of supporting ordinary life on Earth, much less one light enough, reliable enough, and powerful enough to drive a crewed spacecraft for decades. A fusion engine would need to create and control extremely hot plasma while surviving vibration, radiation, magnetic forces, and uninterrupted operation. Its fuel must be stored. Its reaction chamber must avoid damage. Its engines must restart when the ship is already light years from every repair facility. Another family of ideas removes much of the energy source from the spacecraft itself. A light sail uses the pressure of photons. Sunlight can push a reflective surface without consuming onboard propellant, though the force is small. Given enough time and an extremely light spacecraft, that constant pressure can build speed. For a voyage to another star, the sail might instead be driven by a powerful beam produced near Earth or elsewhere in the solar system. Lasers could focus energy onto a thin reflective sail, accelerating a small craft without forcing it to carry the entire energy source and fuel supply on board. The ship becomes lighter because the machinery providing the push remains behind. A sufficiently powerful beam might accelerate a tiny probe to a significant fraction of light speed, making a journey to Alpha Centauri possible within decades, rather than millennia. But a probe and a human vessel are separated by an enormous gap. A wafer-like spacecraft can tolerate a design that would be useless for people. It does not need air, water, living space, farms, gravity, or thick shielding. A sail large enough to push a crewed ship would be vast, thin, and vulnerable. The beam would have to remain aimed across an increasing distance while the sail accelerated away. The sail must reflect most of the incoming energy, because absorbing even a small fraction could overheat and destroy it. Even if such a beam successfully accelerated the ship, it might not be available at Alpha Centauri to slow it down. A spacecraft arriving at a fraction of light speed cannot simply deploy a parachute. It would need another method of braking: onboard engines, interaction with the destination star's light or magnetic environment, or a mission designed only to pass through without stopping. After decades in darkness, Alpha Centauri would grow brighter, rush past, and begin fading behind them, while the ship continued into interstellar space. The propulsion system must therefore be judged not only by how fast it can leave, but by whether it preserves a way to arrive. The ship must gain interstellar speed, survive the crossing, then remove nearly all of that speed without exhausting its power or destroying its passengers. A ship accelerating at a small, steady rate might give the crew a weak sense of gravity, pulling them toward one end of the habitat. Stronger, continuous acceleration could create a more Earth-like weight, but the energy requirement would become even greater. The vessel may instead rotate, using the motion of a large ring or connected habitats to press people toward an outer floor. Artificial gravity would protect muscles, bones, circulation, and perhaps development across generations, but rotating structures add bearings, seals, balance problems, and moving components that must survive for the full voyage. Every system changes the mass, power use, repair burden, and shape of the ship. The ship becomes a network of compromises in which solving one danger quietly creates another. Reliability may matter more than raw speed. A vehicle that can reach Alpha Centauri in 50 years is useless if its engine destroys itself. After 10, a slower design that can be repaired with simple tools may offer a better chance of completing the crossing than a perfect machine, whose components are impossible to reproduce on board. The crew would need workshops capable of manufacturing electronics, mechanical parts, pipes, seals, lenses, pumps, and perhaps entirely new machines from stored raw materials. For a multi-generational voyage, the propulsion system becomes part of the culture of the ship. Children may grow up learning the sounds of pumps and reactors before they learn what rain once sounded like on Earth. It would organize the lives of everyone inside it. Before departure, the design would be tested for years in the solar system. Smaller versions could travel to the outer planets. Full engines might operate without crews, while engineers study how materials age under constant heat, radiation, and vibration. Yet no test near Earth could reproduce a century without rescue. A prototype can be watched, repaired, and replaced. The interstellar ship must continue after the people who built it are gone. Redundancy would be essential. Several power systems could share the load. Multiple engines might allow the vessel to continue after one fails. Critical controls would need physical backups rather than relying on one computer network. But redundancy adds more mass, and the spacecraft cannot carry an unlimited copy of itself. At some point, the builders must decide which failures can be repaired, which can be survived, and which would leave the mission with no future. The terrifying part of designing the ship is not finding one engine powerful enough to begin the journey. It is accepting that the entire vessel must remain a functioning civilization, while that engine, its power source, and every supporting system age together in a place where help can never catch up. The launch would therefore come only after generations of work on Earth. Factories in orbit might assemble the structure. Fuel could arrive across many missions. Habitats would be sealed, tested, opened, and rebuilt. Closed ecosystems would operate for years before anyone trusted them with a population that could not return. The ship might circle the sun, while engineers wait for the right departure path toward Alpha Centauri. Then, the final supplies would arrive. The crew would board. The engines would begin their long acceleration, not as one violent explosion, but as a controlled force continuing day after day. Earth would slowly become a world behind them. The vehicle that humanity had never needed before would finally exist, carrying enough energy to leave the solar system and enough life to make the destination matter. And once the impossible spacecraft had been imagined as a self-repairing world built around an engine that might need to run for years, its departure could begin with the last familiar planets passing quietly behind it. It would begin close to Earth, surrounded by the world that built the ship. Cargo vehicles would move between the surface and orbit, carrying food, equipment, fuel, raw materials, and the final people who had chosen to leave. Engineers would inspect systems already tested for years. Families would exchange messages while the delay was still measured in seconds. Clouds would move across blue oceans. City lights would appear on the night side. The moon would cross the distance beyond them, familiar and close compared with everything ahead. There might be no single violent launch once the ship was assembled in space. The acceleration could be gentle enough for the structure and the people inside, continuing steadily while Earth became smaller behind it. The first days would still feel connected to home because the planet would remain visible and communication would arrive almost immediately. The ship would pass the moon's orbit and move into a region where no human settlement waited ahead. Earth would begin shrinking from a world into a bright sphere, then into a point that could be covered by a hand against the glass. A course toward Alpha Centauri could not be drawn as a simple straight line from Earth. The ship would begin while Earth and the other planets were moving around the Sun, carrying their own orbital speed. Engineers would choose the departure time so that the spacecraft entered the correct path while avoiding planets, asteroids, and unnecessary changes in direction. Alpha Centauri is not fixed against the sky. Its stars travel through the galaxy while the Sun does the same. The spacecraft would aim not toward where the system appeared at departure, but toward where it was expected to be many years later. During the early phase, the Sun would still dominate the journey. Its gravity would pull on the vessel, its light would provide energy, and its position would remain the clearest guide to the world behind. Depending on the engine, acceleration might continue through the inner solar system. A fusion drive or nuclear system could push the ship under its own power. A light sail might depend on an immense beam sent from near Earth, with the force arriving from a machine that would remain behind forever. Ground stations would follow the ship's position, compare it with the planned route, and send corrections while there was still time to respond. Small errors made near Earth could grow into enormous misses after light years of travel. The crew would check the engines, cooling systems, navigation sensors, habitats, and closed ecosystem again and again. A problem discovered early might still allow a return or a rescue mission. The ship would pass the distance of Mars, then Jupiter, Saturn, Uranus, and Neptune. Most of those planets might remain far away, visible only as bright points through instruments. Yet, their paths would mark the increasing separation from Earth. Beyond it, sunlight would be far weaker than it is near Earth. Solar panels would need vast collecting areas, or would no longer provide enough power for a large human vessel. The ship's reactors, fuel, and internal systems would become responsible for nearly everything. Inside, life would depend on manufactured conditions. Light for crops would come from lamps, heat would come from machinery and reactors. Air would move because pumps continued working. Water would remain available because the ship recovered it from breath, waste, and daily use. As Saturn's orbit fell behind, the familiar arrangement of the solar system would begin flattening into one direction. Earth, Mars, Jupiter, and the inner inner worlds would appear close together near the Sun, because distance would compress their positions against the sky. At Uranus and Neptune, the ship would already be farther from Earth than any crew had traveled. Communication delays would be measured in hours rather than minutes, even though the spacecraft had covered only a tiny fraction of the route to Alpha Centauri. The voyage across the planetary system might require months or years, depending on acceleration. Yet the stars ahead would remain almost unchanged. The ship could cross the distance from Earth to Neptune many times and still make little visible progress toward its destination. Neptune is often treated as the edge of the solar system because it is the outermost major planet. But passing it would not mean that the Sun's environment had ended. Beyond Neptune lies the Kuiper Belt, a broad region containing icy bodies dwarf planets, and remnants left from the formation of the planetary system. The ship would not pass through a dense field of closely packed rocks. The distances between large objects are enormous. Most of the region would look as empty as the space before it. A small course correction made early could prevent a dangerous approach years later, and telescopes would continue searching the space ahead for known and unknown objects. At interstellar speed, the safest route would avoid even distant uncertainties. Its orbit is tilted and stretched, and the ship would not change course merely to pass one last famous world. Yet the idea of Pluto could still carry emotional weight. It belongs to the map children learn on Earth, one of the final named places before the solar system becomes less familiar. Beyond the Kuiper Belt, the structure of the Sun's influence becomes harder to see. The Sun continuously releases a flow of charged particles known as the solar wind. It travels outward in every direction, carrying magnetic fields far beyond the planets. Together, this creates the heliosphere, a vast bubble formed by the Sun inside the surrounding interstellar medium. Earth's orbit lies deep inside it. Neptune remains inside it. Even the distant Kuiper Belt is largely enclosed by the environment created by our star. The spacecraft would therefore leave the planets before it truly left the region shaped by the Sun. At a distance far beyond Neptune, the outward solar wind begins to slow as it meets pressure from the material between stars. The region becomes more disturbed, and the clean picture of the Sun sending particles outward gives way to a boundary shaped by two environments pressing against each other. The final boundary of the heliosphere is called the heliopause. Voyager 1 crossed it in 2012, after traveling for more than 3 decades. Voyager 2 crossed several years later at a different point, revealing that the boundary is not a simple perfect sphere around the Sun. A fast human vessel could reach it far sooner, but no window would reveal the exact moment. Instruments would see the transition through particles, magnetic fields, and radiation. The familiar flow from the Sun would weaken, while material from interstellar space became dominant. For the first time, a human crew would travel outside the protective bubble created by its own star. The phrase interstellar space might suggest that the solar system had been fully left behind, but the truth is more complicated. The heliopause marks the edge of the solar wind's bubble, not the end of the Sun's gravity. Far beyond it, distant icy objects may remain loosely bound to the Sun in the enormous region known as the Oort cloud. Some estimates place its outer extent a meaningful fraction of the distance to the nearest stars. The spacecraft could enter interstellar space while still passing through the most distant gravitational outskirts of its home system. Instead, the Sun would release the ship, layer by layer. The crew might mark the heliopause crossing with a ceremony, yet the event would feel different from landing on a world. No surface would receive them. No atmosphere would surround them. They would simply continue through a region where the material outside no longer belonged mainly to the Sun. The planet that had filled the first windows of the journey would disappear into the glare around its star. Even powerful telescopes aboard the ship might struggle to separate it from the other worlds near the Sun. The Sun itself would remain bright for a long time. It would still outshine most stars behind the ship, but distance would steadily reduce its power. The broad disk seen from Earth would shrink until it became a point. The change would be gradual enough that no one could identify the exact day when the Sun stopped looking like a sun. Eventually, it would become one star among many. The people aboard might still know which one it was because computers marked its position. They could point cameras toward it and receive transmissions arriving from the same direction. But the light would no longer reveal oceans, clouds, forests, or cities. Everything humanity had built before the ship departed would fit inside one pale point. During the early years, many passengers would remember Earth directly. They would remember weather, open air, changing seasons, and the feeling of sunlight that had traveled only minutes from the Sun. Messages from Earth would continue arriving, delayed by the growing distance. During the first months, the delay might remain small enough for conversations spread across a day. Later, questions and answers would be separated by weeks, then months. A celebration received on board might describe an event that had already become old news on the planet. A warning from the ship could reach mission control long after the crew had repaired the problem, or accepted that it could not be repaired. Ground engineers could offer knowledge, but they could no longer guide every emergency in real time. The people aboard would become responsible for decisions that no one on Earth could review before the consequences arrived. The sun's magnetic bubble provides some influence over the charged particles moving through the region. Outside it, the spacecraft would face the interstellar environment more directly, including energetic radiation that could pass through the hull and slowly damage electronics, materials, and living tissue. Shielding would reduce the exposure, but shielding has mass, and no practical design could surround the entire ship with an unlimited barrier. Water tanks, storage areas, and dense equipment might be arranged around living spaces to add protection. The crew would monitor doses accumulated across years, knowing that the journey itself could not be paused while the danger passed. There was no nearby station to reach, no planet to hide behind, and no natural shelter within practical distance. The engines might still be running during part of this departure, building speed as the ship crossed the heliosphere. If so, the crew would feel the same gentle direction inside the habitats day after day. The vessel would enter a long coasting phase, carrying the velocity gained near the solar system while conserving fuel and reducing wear on the main engines. The sudden absence of thrust could change life on board. Rotating habitats might continue providing artificial gravity, while non-rotating sections return to weightlessness. Reversing the journey would require removing the ship's enormous outward speed, accelerating back toward the sun, and preserving enough power to slow again near Earth. The mission crossed a point of no return, long before anyone could identify one exact location. The last familiar planets did not vanish all at once. The sun did not become a star in one night. Communication did not fall silent with one broken signal. Home faded gradually, while the ship continued functioning inside its own sealed environment. A door can be closed and remembered. A world shrinking for years remains present just enough to reveal how much is being lost. Eventually, the navigation display would show that the planetary system was far behind and the heliopause had been crossed. Alpha Centauri would still remain almost the full journey ahead. The great departure from the solar system, which no human crew had ever completed, would represent only the opening movement of the voyage. Behind the ship lay the only inhabited world anyone knew. Ahead lay several light years without a planet, station, or safe harbor. The spacecraft had left the protection of one star, but had not yet come close to another. And once the final influence of the solar system had weakened behind the ship, the journey could no longer be measured by departing planets or crossed boundaries, only by the years of darkness still waiting between the stars. There would be no road stretching ahead, no landscape moving past the windows, and no visible marker showing how much of the journey had been completed. The stars would remain fixed against the black sky for long periods, changing so slowly that even a ship moving at extraordinary speed might appear almost motionless. Lights would brighten and dim according to an artificial schedule. Meals would be prepared, equipment checked, crops harvested, filters replaced, and children taught lessons about worlds they had never seen. The ship would create its own days because the natural rhythm of Earth had been left behind. The sun behind them would remain visible as a star, but it would no longer cross a familiar sky. Alpha Centauri ahead would grow brighter over the years. Yet for much of the voyage, it would still resemble one distant point among many. A vessel traveling at a significant fraction of light speed would cross millions of kilometers every minute. Even then, the distance covered during one day would remain almost meaningless compared with the full journey. The crew might watch numbers change on navigation displays, while the view outside seemed frozen. The ship would move farther than every earlier human journey combined, yet Alpha Centauri would still look unreachable. On Earth, travel is experienced through movement. Roads pass beneath a vehicle. Clouds move beside an aircraft. Waves rise around a ship. Even a journey through the solar system can be divided by planets, moons, and orbital boundaries. The spacecraft would use star trackers, pulsars, internal clocks, and repeated measurements of its own motion. Computers would compare the real path with the one calculated years earlier. A tiny error in direction could become enormous by the time the ship reached the destination. If the vessel missed Alpha Centauri by a small angle, it might pass millions or billions of kilometers from the intended arrival point. Correcting that mistake late in the journey could require more energy than the ship had available. The crew might never feel the correction, yet it could decide whether the ship entered the Alpha Centauri system or passed through the darkness beside it. Alpha Centauri A and B orbit one another, while Proxima Centauri travels much farther from the pair. Any planet in the system would also be moving around its star. It would aim for an encounter between two moving paths, calculated decades before arrival. New observations from Earth could improve the estimate during the early voyage, but those messages would arrive increasingly late. Eventually, the ship would have to trust its own instruments. Only the numbers would reveal that the future destination was slowly moving away from the path of the ship. For most people aboard, the journey would be experienced inwardly rather than through space outside. The vessel might include several habitats: work areas, farms, storage sections, workshops, medical rooms, and shielded compartments. These enclosed spaces would become neighborhoods, workplaces, and landscapes. They would recognize small vibrations in the walls and changes in the sound of ventilation. A new noise from a pump could attract attention more quickly than any change among the stars. There would be no open door leading outside, no unplanned walk, no private distance greater than the size of the ship. Every argument, friendship, illness, and loss would happen inside the same sealed structure, carrying everyone toward the same destination. A child born halfway between the stars would not have volunteered to leave Earth. The ship would be the only world that child had ever touched. Earth could become emotionally distant long before Alpha Centauri became close. The mission's purpose would have to survive this change. Education would carry more than technical knowledge. It would explain why the ship existed, where it was going, and why generations of people were expected to maintain a plan begun before they were born. Some passengers might believe that reaching Alpha Centauri justified every sacrifice. Others might question whether a destination chosen by people long dead should control the lives of everyone still aboard. By the time such arguments became serious, the ship might be too far from Earth and moving too quickly for return to be practical. Continuing forward could be the only option even for those who no longer believed in the mission. It would require a society capable of remaining stable inside isolation. Rules would need to change as the population changed. Leadership could not depend forever on instructions from Earth. Medical decisions, resource limits, education, reproduction, and conflict would all become local responsibilities. The ship would slowly become independent, not because it declared independence, but because distance made every outside authority too slow to respond. Communication would continue, though it would no longer resemble conversation. A message sent after 1 year of travel might require months to reach Earth, depending on the ship's speed and distance. Later, the delay would grow into years. Near Alpha Centauri, a signal would take more than 4 years to return to the solar system. A person asking a question might receive the answer during a completely different stage of life. Earth would become a source of historical transmissions rather than immediate help. Elections, discoveries, disasters, Births and deaths would be old by the time the ship learned about them. The crew could send its own reports, knowing that Earth would hear them years later. The connection would remain real, but it would lose the speed required to shape daily life. It would be the natural condition between messages. The ship might receive a transmission, then wait months or years for the following. 1. During that time, there would be no way to know whether Earth was silent, whether an antenna had failed, or whether the signal was still crossing the distance. A technical delay could feel like the disappearance of an entire planet. The emptiness outside would also change the practical meaning of rescue. Within the solar system, another spacecraft might eventually reach a stranded crew, though the journey could take months or years. Between the stars, no rescue vehicle launched after an emergency could catch a ship already traveling at interstellar speed without an even more powerful propulsion system. The ship would carry the only tools, materials, medicines, and expertise available anywhere nearby. A failed component could be remade in a workshop if the raw materials and knowledge existed. A damaged electronic system might be redesigned rather than replaced with an identical part. The crew would need to understand the ship deeply enough to change it. Over decades, the vessel would no longer remain exactly as it was built. Sections could be rebuilt, with newer methods developed on board. Machines might be simplified because simple systems were easier to maintain. Other systems could become more complex as the community learned to produce better tools. This would be unavoidable because no machine can operate for generations without change. Materials weaken, seals harden, pipes corrode, electronics fail. Radiation alters components slowly, and repeated heating and cooling create stress. The crew would replace filters before they failed, inspect pressure walls for damage, test backup power, and monitor the closed ecosystem for small changes. A microorganism harmless on Earth might behave differently inside a sealed environment where there was nowhere else for it to go. Earth contains countless systems that support human life without anyone noticing them. Oceans move heat. Soil contains vast communities of organisms. Weather carries water. Ecosystems recover through diversity and scale. The spacecraft would imitate only a small part of that complexity. Reactors or other long-lived sources would provide electricity for light, heat, air circulation, water processing, computers, workshops, medical systems, and perhaps propulsion. If power production declined, the ship could not simply reduce comfort and continue normally. Lower power might mean less food, weaker air circulation, fewer repairs, and reduced shielding from active systems. Backup systems would need to remain unused, yet ready for decades. A reactor started halfway through the voyage might contain parts manufactured before the oldest living passenger was born. The people aboard would have to trust both the original design and the care of every generation that maintained it. A door seal, water valve, computer cable, or structural joint could carry a history longer than one human life. Water would pass through people, crops, tanks, and filters repeatedly. The ship would be a closed loop moving through a region that offered almost no new resources. That closed world would still need change. People require privacy, variety, celebration, and meaning. A perfectly efficient habitat could still fail if life inside became unbearable. The vessel might create parks beneath artificial light, rooms with changing projections, or quiet spaces where the machinery was less audible. Music, stories, rituals, and games would become as necessary as spare parts because the mission could not survive if the community lost the desire to continue. Stars would remain beautiful, but their stillness could become oppressive. The same constellations would appear for years, slowly changing as the ship moved through three-dimensional space. Some nearby stars would shift slightly against the distant background. Familiar constellations would deform, revealing that the patterns seen from Earth belonged only to one viewpoint. Earth's constellations would no longer guide seasons or stories in the same way. The crew might create new names for the sky seen from the ship. A year originally measured Earth's orbit around the Sun. On the ship, Earth years might remain useful for records, but they would no longer match anything happening outside. The community could preserve Earth's calendar, invent a mission calendar, or divide time according to distance traveled. The destination would become the only large event moving slowly closer. Navigation systems could display the remaining distance, but watching that number every day might make the voyage feel longer. The crew might hide it from ordinary life and mark only major milestones. The point where Alpha Centauri's light reached them in less time than the Sun's. The midpoint would be especially important if the ship had accelerated through the first part of the voyage and needed to begin slowing during the second. The force that had pushed everyone away from Earth would begin resisting the motion carrying them toward Alpha Centauri. Outside, the ship's entire relationship with the destination would reverse. It would no longer be trying to gain speed. It would be trying to lose enough speed to remain in the system ahead. Yet before that stage, most of the voyage could remain a long coast through darkness. The engines would be quiet. The stars would shift slowly. The ship would continue at a speed that would cross the solar system quickly, while the destination still required years. This is where the true scale of interstellar space would become most difficult to ignore. The emptiness was not merely a lack of objects. It was a distance so large that a self-contained human world could live through decades of history without reaching anything. Generations might change, while the external view barely did. The ship could experience births, deaths, inventions, arguments, repairs, celebrations, and entire lives between two stars. The journey would become more than transportation. It would become an era. And still, the space outside would not be perfectly empty. Scattered atoms would drift through it. Energetic particles would cross the ship's path. Tiny grains of material, nearly invisible against the darkness, would wait ahead. At ordinary speed, they would mean almost nothing. At interstellar speed, the ship would meet them with the force of a weapon. And once the long interstellar night had revealed how little the crew could see, use, or escape in the space between stars, the few particles hidden inside that apparent emptiness became the next danger moving directly toward the ship. Interstellar space is far emptier than any vacuum humans can create on Earth. But it is not perfectly empty. Thin gas stretches between the stars, mixed with microscopic grains of carbon, silicates, metals, and ice. Most of those grains are smaller than anything a person could see without a microscope. Some are no larger than smoke particles, scattered so widely that a slow spacecraft might pass through them without serious harm. A grain does not need an engine or a sharp edge to become dangerous. The ship supplies the energy through its own motion. When a spacecraft meets a particle while traveling at a meaningful fraction of the speed of light, the collision happens so quickly that neither object behaves like an ordinary solid. The grain and part of the surface can flash into hot gas and plasma. Material can melt, vaporize, and spread through the layers behind the impact point before the crew has time to register what happened. The danger would not appear as a field of rocks visible through the windows. There might be nothing for cameras to show. The first sign could be a brief signal from a sensor, a change in temperature, or a tiny loss of performance in equipment facing forward. A ship crossing more than 40 trillion kilometers would expose its leading surfaces to the interstellar medium for decades. A single microscopic particle might remove almost nothing, yet thousands or millions of impacts could slowly roughen, weaken, and erode the material. The problem is not only one dramatic collision, it is the accumulation of damage across a journey too long for the ship to avoid every particle ahead. Individual hydrogen atoms are harmless at ordinary relative speeds. At interstellar velocity, however, they strike the forward surface as a continuous stream of energetic particles. Heavier atoms can penetrate materials, disturb their structure, and produce secondary radiation when they collide with the shield. The spacecraft would experience the thin, interstellar gas less like a gentle cloud and more like a narrow beam aimed constantly at its front. Doubling the speed would not simply double the energy of an impact. The energy rises much more quickly, making the desire for a shorter journey collide directly with the need for survival. A ship, traveling slowly, would spend longer in darkness, but meet the particles with less force. A ship traveling quickly would reduce the years of life support and isolation, while turning smaller pieces of matter into greater threats. The direction of travel would give the spacecraft a vulnerable face. Most of the harmful material would arrive from ahead because the ship would be moving into it. The leading end could therefore be shaped around protection, with the inhabited sections placed farther behind. The vessel might resemble a long structure rather than the balanced shape often imagined in science fiction. Engines, habitats, radiators, and communication equipment would not all face the same way. The forward end would carry layers whose main purpose was to be damaged instead of the people and machinery behind them. A simple, thick wall could absorb some impacts, but every additional layer would add mass. That mass would have to be accelerated at departure and slowed near Alpha Centauri. A shield, heavy enough to survive decades of erosion, could demand more fuel, larger engines, and stronger structural supports, making the entire mission more difficult before it began. Modern spacecraft already use forms of spaced shielding against micrometeoroids and orbital debris. A thin outer layer breaks an incoming particle apart, spreading the impact into a wider cloud before it reaches the stronger wall behind. Several separated layers can reduce the concentration of energy, allowing a lighter system to protect against objects that might penetrate one sheet of metal. Its forward shield might contain sacrificial plates, ceramics, foams, fibers, or layers of material chosen to melt and fragment in controlled ways. Empty gaps between those layers could allow debris from an impact to spread before meeting the next surface. Tanks of water or stored raw material might add further protection behind them. Its outer face would gradually become cratered. Microscopic pits could overlap. Heat could alter the material around each impact. Repeated strikes might create cracks that instruments would need to detect before they grew into a larger failure. A ship designed for generations might carry spare shield panels or manufacture new ones from stored metal and other materials. Robotic systems could move damaged plates away and place fresh layers at the front without exposing people outside. The space between the Sun and Alpha Centauri contains a very thin local interstellar environment, but its exact structure is not known at every point along the path. Dust may not be distributed evenly. Small clouds, filaments, or regions shaped by magnetic fields could carry different concentrations of particles. A small robotic craft could travel ahead as a pathfinder, sending measurements backward. But if the main ship were following at high speed, warnings would arrive with limited time to respond. The pathfinder would need to remain far enough ahead to provide useful notice while carrying sensors capable of finding particles that were themselves extremely small and dark. A particle only a few millimeters across could be far more damaging than the microscopic dust encountered more often. Yet, it would reflect very little light. At interstellar speed, even a detection made thousands of kilometers ahead might leave only a fraction of a second for action. Its mass and velocity would resist rapid changes. A sudden maneuver could stress the structure, disturb rotating habitats, redirect radiators, or move people and equipment inside. The safest response might not be to dodge each object, but to build the forward protection so that most expected impacts could be survived. A design can be tested against known particle sizes and estimated densities. It cannot prove that no larger grain lies somewhere along 40 trillion kilometers of path. The mission would cross such an enormous volume of space that a low probability would never become absolute safety. A broad vessel presents a larger target. Large rotating habitats, wide sails, and exposed radiators increase the area that can be struck. A narrow profile facing forward reduces risk, but many systems need surface area to function. The spacecraft might fold, rotate, or rearrange components after reaching cruise speed. A sail used near the solar system could be discarded or placed behind protective structures. Radiators could extend sideways where the forward shield offered less protection, though angled impacts and secondary fragments would still need consideration. If the protected face turned away from the direction of travel, surfaces never designed to meet the interstellar stream could be exposed. A navigation error that changed only the spacecraft's angle rather than its route might allow gas and dust to strike delicate equipment. Star trackers, gyroscopes, and distant reference points would help keep the shield facing forward. Backup systems would be essential because the ship could not afford to drift unnoticed for days. A microscopic grain would not move the whole ship by much, but a larger strike could create torque, vibration, or an uneven release of material from the shield. Sensors would need to distinguish normal impacts from structural changes that required a response. A collision powerful enough to scar the outer layers could be absorbed across structures far from the habitat. The event might appear only as a warning on a maintenance display. Yet behind that calm signal, material that could never be recovered would have been removed from the ship. Robotic cameras could inspect the forward surfaces from protected positions. Ultrasonic sensors, embedded fibers, electrical circuits, or pressure layers could reveal cracks and penetration without exposing anyone to the outside environment. The greatest danger would be a penetration that continued beyond the sacrificial layers. A fragment or plasma cloud entering the vessel could damage cables, cooling lines, fuel systems, computers, or pressure walls. A small hole into a vacuum is not always an instant catastrophe, but any leak inside a closed interstellar habitat would demand attention. The ship might be divided into many sealed sections so that one damaged compartment could be isolated. This separation would make the vessel heavier and more complicated, but it would prevent one narrow impact path from opening the entire living world to space. Power cables, water pipes, communication links, and control networks could follow separate routes. If one section were cut, another would continue carrying the load. Important equipment might be duplicated in different protected areas. When energetic atoms and dust meet the shield, they can create showers of secondary particles and high-energy radiation within the material itself. A thicker barrier does not always solve every form of radiation in a simple way, because collisions inside the shield can generate new particles that continue deeper. Hydrogen-rich substances, such as water or certain plastics, can be useful against some radiation. Dense metals may stop one threat while creating additional secondary radiation under another kind of impact. Storage tanks could surround living areas, turning a basic supply into shielding. Food stores, waste, fuel, and raw construction material could also be arranged between the crew and the outside environment. If a water tank used for protection became emptier, another material might need to replace its shielding role. The ship could move stores around over time, maintaining safe layers around sleeping areas and emergency shelters. During an unusual event or evidence of a larger impact ahead, people could gather there. Yet, there might be little warning. Unlike a solar storm, a dust collision would not announce itself across hours. Protection would need to exist before the threat arrived. The crew would know that the darkness ahead contained matter they could not see. Sensors might record small strikes every day or every week, each one proving that the empty space outside was touching the ship. That change would be necessary for life on board. No community could remain terrified by every microscopic impact across decades. Procedures would turn uncertainty into tasks that could be measured and completed. The ship would keep a remaining protection estimate, though the number could never be perfect. Models would compare the actual damage with the expected rate and predict whether the forward layers could survive until deceleration began. If the erosion became worse than planned, the crew would face difficult choices. Reducing speed would lower future impact energy, but extend the journey. Extending the journey would consume more food, energy, spare parts, and human lives. Adding new shielding from onboard materials could protect the vessel but remove resources intended for repairs or settlement at Alpha Centauri. Every solution would spend something that could not easily be replaced. The threat from dust would therefore reach far beyond the outer hull. It could change the mission's speed, schedule, population plans, and chance of building a home after arrival. Protection used during the crossing might be material no longer available at the destination. A ship that survived by consuming too much of itself could reach Alpha Centauri, unable to begin again. This is why the vessel could not be designed as a shell carrying passengers. It would have to be a living balance between protection, propulsion, resources, and time. The shield at the front would preserve the machines behind it, but those machines would preserve the people, the air, the water, and the small biological world that made the journey worth surviving. Outside, the interstellar medium would continue striking the ship without intention or pause. Inside, every breath would depend on systems protected by layers that were slowly being worn away. And once the forward shield had revealed how much machinery and material were required simply to keep the darkness from entering the vessel, the deeper challenge became keeping an entire human world alive behind it for as long as the crossing demanded. Behind the shielding, the ship would contain everything its passengers needed, but almost nothing could be wasted. Air would not arrive from an atmosphere outside. Water would not fall from clouds, flow through rivers, or wait beneath the ground. Food could not be delivered by another vehicle once the solar system had faded behind them. Every basic part of life would have to circulate through machines, tanks, crops, microorganisms, and human bodies again and again. The vessel would not carry supplies for the entire crossing, in the ordinary sense. Even a large ship could not simply store enough fresh air, drinking water, and prepared meals for decades or generations without becoming impossibly massive. It would need to recover what its passengers used and return it to the system with as little loss as possible. People would inhale oxygen and release carbon dioxide. Plants could use some of that carbon dioxide during growth, while mechanical scrubbers remove the rest. Oxygen would be produced through biological processes, chemical systems, or the splitting of water. Sensors would continuously measure the balance because the air could feel normal, while a dangerous change developed too slowly for anyone to notice. On Earth, a small amount of contamination can disperse into an enormous sky. Inside a spacecraft, every vapor remains within the same limited volume until a filter captures it or a reaction changes it. Cleaning fluids, plastics, electronics, crops, human skin, and industrial work would release traces of material into the air. Many would be harmless in small amounts, but years of accumulation could turn an overlooked chemical into a serious problem. Ventilation would therefore do more than make the cabins comfortable. It would carry air through filters, prevent pockets of carbon dioxide from forming, control humidity, and move heat towards systems able to release it. A failed fan could affect an entire section of the ship long before the silence of that fan seemed dangerous. Water would follow an equally careful loop. It would be recovered from breath, sweat, washing, food preparation, plant growth, and waste. Filters and treatment systems would remove particles, chemicals, and microorganisms before the water returned to storage. There would be no reason to think of it as old or used once purification was complete. Yet the psychological adjustment might take time for the first passengers. Later generations would never have known another system. For them, water would naturally belong to a cycle contained within walls. Moisture could become trapped in materials, Small leaks could release vapor into spaces where recovery was difficult. Chemical processes could bind water into waste that was not easily reused. Each loss might be tiny, but the journey would be long enough for tiny losses to matter. The ship would carry reserves, though those reserves would also serve other purposes. Water stored around the habitats could add radiation protection and absorb some of the energy from impacts. Moving it from one tank to another might change the balance of shielding, life support, and even the spacecraft's motion. Stored meals could support the early years and provide emergency reserves, but a multi-generational crossing would require agriculture. The ship would need to grow a meaningful share of its own food beneath artificial light using controlled water, nutrients, temperature, and atmosphere. Plants could grow in nutrient-rich water, mist, or engineered substrates that were easier to clean and monitor. Their roots would be inspected for disease. Their leaves would be measured for changes in color and growth. Light cycles would be chosen for efficiency rather than for the rhythm of any season. Pumps would move water, lamps would provide energy, sensors would measure acidity, nutrients, humidity, and gases. Pollination might be performed by insects, airflow, machines, or people. Seeds would be stored with genetic diversity in mind, because losing one crop variety could remove traits needed decades later. The crops would need to provide calories, protein, vitamins, oils, fibers, and useful materials while growing reliably in limited space. Fast-growing plants might support daily needs, while slower crops added variety and stability. Algae, or microorganisms, could produce food efficiently, though a diet designed only around efficiency might be difficult for people to accept across an entire lifetime. Food connects people to memory, culture, family, and celebration. The first crew might bring recipes from Earth and adapt them to ingredients available on board. Later generations could create dishes that had never existed on any planet, shaped by the crops and machines of the ship. Human waste, dead plants, spoiled food, damaged biological material, and organic residue could be processed into water, gases, and nutrients. Nothing would disappear merely because it was moved into a container. Storage space was limited, and every useful element locked inside waste was an element missing from the active ecosystem. It would involve mechanical separation, heat, chemical treatment, microbial digestion, and careful testing before recovered material returned to crops or water systems. A failure could allow contaminants to pass through several connected loops. A mistake in waste treatment could affect the farm. A farm imbalance could alter the air. A water problem could reduce shielding reserves. A power shortage could weaken all three at once. The ship would behave less like a collection of separate rooms, and more like one organism whose organs had been built from metal, glass, wiring, and living tissue. Without continuous energy, lights would fade over the crops, pumps would slow, air would stop circulating, and temperatures would begin moving away from safe limits. The cold outside would not instantly freeze the ship, because its own systems and occupants produced heat, but that heat would become uneven and increasingly difficult to control. For this reason, essential equipment would need multiple layers of backup. One air processor could fail while another carried the load. Sections of the farm could operate independently. Water treatment might use several smaller systems rather than one irreplaceable machine. Machines age even when they appear to work normally. Bearings wear, seals crack, filters clog, pipes collect deposits, sensors drift away from accurate readings. Computer memory is damaged by radiation. Materials become brittle after years of stress. Workshops would turn stored raw material and old components into new parts. Simple mechanical pieces could be machined, printed, melted, or reshaped. More advanced electronics would be harder to reproduce, requiring specialized materials and manufacturing environments. Instructions, engineering records, medical information, agricultural data, and scientific libraries would be copied across several protected systems. Printed references might remain available in case digital storage failed. Training could never end, because every generation would need people capable of understanding machinery designed before they were born. Children would learn ordinary language, mathematics, history, and art. But they would also grow up surrounded by the systems that kept them alive. They might visit the farms as part of school, help inspect water loops, and learn why opening the wrong valve could affect people in another habitat. A voyage lasting several generations could not treat population as an unplanned result of private life alone. The number of people would affect food, oxygen, living space, genetic health, education, and the amount of work needed to maintain the vessel. Rules designed on Earth might not remain accepted decades later. The people living with them would question who had the authority to decide family size, resource access, medical priorities, and leadership. A stable ship would need more than strict control. It would need trust, fairness, and a way for its society to adapt without damaging the life support systems on which every disagreement depended. The same closed environment that encouraged cooperation could intensify small tensions. People would meet the same neighbors repeatedly, use the same shared spaces, and carry old arguments into a future with nowhere else to go. Habitats might include quiet rooms, personal cabins, gardens, and areas designed to feel separated from the machinery. Digital environments could offer larger virtual spaces, though they could not replace physical movement and human contact forever. Depression, grief, loneliness, fear, and loss of purpose could reduce a person's ability to care for equipment or others. A community that treated these only as private weakness could place the entire voyage at risk. Some people would die from age, illness, accident, or conditions the medical system could not cure. There would be no cemetery outside, and no possibility of returning a body to Earth. Organic material might eventually be returned to the ship's biological cycle, after whatever ceremony the culture considered respectful. This could be emotionally difficult for those carrying traditions from Earth. Yet later generations might understand it as a final form of contribution to the world that sustained them. Names could be recorded in common spaces. Stories might be preserved alongside maintenance records and scientific data. Children would grow up knowing that many people had lived and died to move the ship only part of the way towards its destination. A generation born near the midpoint might ask why Alpha Centauri mattered more than the life they already had. The ship was safe, familiar, and capable of continuing. A distant planet or star system could offer conditions worse than the habitat around them. The argument would not be theoretical, because the ship's design, fuel, population, and stored resources had all been chosen around an eventual destination. A society that abandoned the mission might discover that the vessel could not support itself forever without new materials. It could recycle much of what people needed, but no system would be perfectly closed. Small losses would accumulate. Rare elements would become harder to replace. Machinery would consume materials that could not always be recovered. Genetic diversity in crops, animals, microbes, and people could narrow. As Alpha Centauri slowly grew brighter, the community would prepare for a transition no living person might have experienced before. Farms designed for the ship could produce organisms intended for habitats at the destination. Equipment might be moved from storage and tested after decades of silence. Before that future arrived, the passengers would continue living in the narrow balance between biology and machinery. The ship could make those processes reliable enough to feel ordinary, and that sense of ordinary life would be one of its greatest achievements. But the people inside would never be entirely alone with their own world. Signals from Earth would still cross the distance behind them, carrying voices, discoveries, warnings, and news from a planet that existed increasingly far in the past. And once the ship had become a complete human world, able to recycle its air, water, food, knowledge, and even its own history, the remaining connection to Earth could survive only through messages that took longer and longer to arrive. A message sent from the ship might reach Earth within minutes or hours, and a reply could return before the end of the day. Families could exchange recordings. Engineers on the ground could study a problem and send advice while the same people were still working on it. The ship would already be moving away, but Earth would remain close enough to participate in daily life. As the distance increased, every message would spend longer crossing space at the speed of light. A question sent in the morning might not receive an answer until days later. Eventually, the delay would stretch across weeks, then months, and communication would stop behaving like conversation. A technical problem would have to be solved on board before anyone on Earth could respond. A medical emergency would not wait for specialists several million kilometers behind. Decisions about power, food, navigation, and human conflict would become local because distance would make outside authority too slow to matter. The ship would continue transmitting reports, but those reports would describe situations that had already changed by the time Earth received them. Mission Control might answer carefully, only to discover that the damaged component had been repaired, replaced, or abandoned months earlier. The people who asked the question might have moved to different roles. A child mentioned in one recording could be noticeably older by the time a reply arrived. The signals themselves would be extremely weak by the time they crossed a meaningful fraction of a light year. Powerful antennas would focus narrow radio or laser beams toward the solar system. The ship would need to know where Earth would be when the signal arrived, not where it appeared when the transmission began. The planet would be moving around the sun, and the sun would be moving through the galaxy with the stars around it. A tiny error could cause the beam to pass beside the solar system. Dust, equipment failure, vibration, or a slight mistake in orientation could interrupt the connection without producing any visible damage on board. Silence would always contain uncertainty. A missing reply might mean that Earth chose not to answer. It might mean that the ground antenna was unavailable, that the message was damaged, or that the return signal was still somewhere between the stars. Earth would continue sending news, scientific discoveries, music, personal recordings, and updates from the descendants of people who had once watched the ship leave. Yet, every transmission would arrive as history. A message received halfway through the journey might describe an Earth from years earlier. Governments could have changed. Cities could have been rebuilt. Entire technologies could have appeared after the signal began crossing space. The ship would learn about the planet in delayed pieces, never knowing its exact present. People aboard might follow a crisis that had already ended, or celebrate a discovery that had become ordinary long before they heard about it. For those who remembered Earth directly, each message could bring back places, voices, and experiences that no longer existed in the same form. The planet would remain emotionally close while becoming physically unreachable. For those born aboard, Earth might feel less like home and more like a distant civilization, sending archives through space. These images would belong to a world they understood only through inherited memory. Over time, even the people sending messages from Earth would become strangers. The first mission controllers would retire. Their replacements would know the ship through records rather than personal relationships. Families on the ground would pass the responsibility for communication to children and grandchildren. A message sent to one person might be answered by someone who had never met them. The connection would survive through institutions rather than individual lives. Words, accents, and expressions evolve across generations. The ship's isolated community might develop its own speech, shaped by technical life, recycled resources, and experiences unknown on a planet. Earth would still have oceans, weather, nations, and a vast population. The ship would have sealed habitats, strict resource limits, and a destination controlling nearly every long-term decision. A recommendation to delay a repair, expand the population, or use a reserve supply could carry different risks when no replacement existed. No declaration would be required. The ship would become politically separate simply because every meaningful decision had to be made before an answer could arrive. By the time Earth learned what had happened, the consequences would already be part of life on board. If the crew made a mistake, there would be no immediate rescue and no outside authority capable of correcting it. If Earth sent poor advice, the people who received it would bear the result years before anyone on the planet learned what happened. Some generations might value every transmission as proof that humanity still remembered them. Others might see Earth as a voice from the past, offering opinions without sharing the danger. Earth might face new crises, new priorities, or new ambitions. Funding and attention could shift. The vast project, once followed by the whole world, might become one distant program, maintained by a smaller group. Years later, a new signal could arrive explaining that antennas had failed, institutions had changed, or political conflict had interrupted the program. The farther the vessel traveled, the larger and more precise its antennas would need to be. A laser link could carry large amounts of data through a narrow beam, but the pointing accuracy would be demanding. Radio would spread more widely, making it easier to detect, but weaker at the receiver. Heat, power, and orientation would need to be managed for every major exchange. Sending a simple family recording across light years would become an engineering operation. Receiving would be equally delicate. The sun would appear as one star among many, and Earth's transmitter would be close to it in the sky. Sensitive instruments would separate the faint artificial signal from background noise. Data could arrive slowly, be checked for errors, and reconstructed over time. A message might take hours or days to download after spending years in flight. When it finally opened, the person speaking could already be dead. This would become normal. The crew would live among delayed voices. Recordings from Earth would mix with older archives stored on board, and the difference between a message and a memory would become less clear. A voice received today might have spoken years ago. A voice recorded before departure might have spoken decades ago. Both would exist as light and data inside the same ship. The passengers would respond, even though the people they answered had already changed. A parent could send a message to a child on Earth, knowing that the child would be older when it arrived. That child could answer, but the reply might reach the ship after the parent had died. The exchange would continue across absences neither side could prevent. For this reason, messages might become longer and more deliberate. There would be little value in sending only a quick question when the answer required years. People might record full accounts of their lives, explain decisions in detail, and include messages for several possible futures. A transmission could contain advice for someone at different ages or instructions to be opened only if certain events occurred. Communication would begin to resemble letters carried across an ocean that no ship could cross. The difference was that the ocean itself was time. The crew might develop rituals around incoming signals. A new transmission from Earth could be announced throughout the habitat. Families could gather. Important scientific or political updates might be played in shared spaces. The ship would hear the planet together, because no one knew when the following message would arrive. The event could bring comfort, but it might also reveal how far the two worlds had drifted apart. Earth's culture would continue producing new music, stories, customs, and ideas. Some would feel familiar. Others could arrive without context, created by a society the crew no longer fully understood. The ship would send its own culture back. Earth would receive recordings of children born between stars, ceremonies created in artificial gravity, new words, repaired machines, and landscapes grown beneath lamps. People on the planet might watch those images years later and realize that the travelers were no longer merely passengers from Earth. They had become a distinct human society. The delay would allow both worlds to witness that change without ever sharing the same present. Each side would know the other only through an earlier version. Near the middle of the voyage, a message from Earth and a message from the ship could cross in opposite directions, carrying decisions made years apart. Neither sender would know what the other had already chosen. Plans could conflict. Earth might recommend one destination in the Alpha Centauri system, while the ship had already committed to another. New observations could reveal a danger ahead, but the warning would need years to reach the crew. The ship's own telescopes would eventually become more important than information from Earth. As Alpha Centauri approached, the crew could study the system from a viewpoint unavailable to astronomers in the solar system. Its stars would separate more clearly. Planets could be observed in greater detail. Dust, magnetic fields, and possible hazards would be measured directly. The flow of useful knowledge would reverse. Earth would begin waiting for the ship's discoveries. Yet those discoveries would arrive years after they were made. The crew could detect a planet, send the result home, and enter the system before Earth learned that the observation existed. For the people aboard, the mission would have moved beyond the guidance of its creators. The connection would remain valuable, but it could no longer lead them. There would be one final threshold in this growing delay. At some point, the signal travel time back to the solar system would become longer than the remaining travel time to Alpha Centauri. A request for advice could reach Earth only after the ship had already arrived. A reply would begin its journey toward a vessel no longer in interstellar cruise. From that moment, every urgent answer would have to come from ahead, not behind. But nothing ahead was yet capable of answering. The crew would turn increasingly toward the destination. Telescopes would watch Alpha Centauri grow, from a bright point into a system with separate stars. Navigation teams would refine the arrival path. Engineers would inspect engines that had been quiet for years and prepare machinery whose failure could undo the entire voyage. The ship had spent decades gaining and carrying speed. That speed had made the crossing possible. It was also carrying the vessel toward the system too quickly to remain there. Communication with Earth could offer calculations, records, and encouragement, but it could not provide a second chance if the braking system failed. By the time anyone on Earth learned that something had gone wrong, the ship might already have passed Alpha Centauri and continued into the darkness beyond. The final messages before deceleration would therefore carry a different weight. They might contain updated plans, personal farewells, and reports sent in case the ship never established a stable connection again. No one would call them final, because the mission expected to continue. Still, every person aboard would understand that the most dangerous machinery on the vessel was about to return to full power. Behind them, Earth would remain a faint star, sending old voices through space. Ahead, Alpha Centauri would finally begin to change from a destination in memory into a place with motion, light, and gravity of its own. And once Earth had become a voice from years in the past, while Alpha Centauri grew into the only future the crew could still reach, arriving safely demanded something harder than crossing the distance. The ship had to surrender the enormous speed that had carried it there. For most of the voyage, speed had been the mission's greatest achievement. Every year of acceleration and every reduction in mass had served one purpose: to make 40 trillion kilometers pass within a human or generational lifetime. Near Alpha Centauri, that same speed would become dangerous. A spacecraft moving at a meaningful fraction of the speed of light could cross the distance between planets in hours or days. It might enter the system, pass its stars, and return to interstellar darkness before the people aboard had time to understand what they had reached. Arrival would therefore begin long before the stars filled the windows. The ship could not wait until it was close and then apply a sudden brake. There is no friction in space capable of slowing a vessel gently, and no atmosphere surrounding an entire star system waiting to catch it. The speed gained during departure must eventually be removed by another physical process. If the ship carried powerful engines and enough propellant, it could rotate so that its thrust pointed against the direction of travel. The engines that once pushed the vessel away from Earth would begin resisting the motion, carrying it toward Alpha Centauri. To an observer outside, the ship would still move forward at extraordinary speed. Inside, the crew would feel the steady force of deceleration as the destination remained ahead. A ship that accelerated gently for years might need to turn near the midpoint of the journey and begin slowing while Alpha Centauri still looked like one bright point. The timing would be unforgiving. Turn too early, and the voyage becomes longer than necessary. Turn too late, and the ship reaches the system with more speed than its engines can remove. Rotating an interstellar vessel would be a major operation. Habitats, radiators, engines, communication systems, and the forward shield might extend across a long structure that could not be turned quickly without stress. For decades, the shield had faced the stream of interstellar dust. During the maneuver, vulnerable surfaces could be exposed unless the vessel was designed to preserve protection from several directions. Artificial gravity might change inside parts of the ship. Fluids would settle differently. Equipment would need to be secured, and the crew might feel a new direction of down while the structure slowly faced its engines toward Alpha Centauri. Then, the machinery that had been quiet for years would have to return to full power. Fuel lines, pumps, magnetic systems, reactor components, valves, and control computers would have aged throughout the crossing. They could be tested in smaller ways, but the complete braking sequence could never be repeated in advance without spending the reserve meant for arrival. An engine that refused to start would not leave the ship safely adrift. It would leave it moving too quickly through the destination. Redundant systems could reduce the risk, although every backup added mass that also had to be accelerated and slowed. The crew would inspect the propulsion system repeatedly, using robots and sensors to search for cracks, leaks, contamination, and changes hidden inside equipment built before many passengers were born. Small test burns would confirm that thrust remained balanced. A slight difference between engines could rotate the ship or pull it away from the planned entry path. At interstellar speed, an error too small to notice in 1 hour could become an enormous miss after months. The burn must also remain gentle enough for the structure. Engines push on one section, while the mass of habitats, water, shielding, machinery, and people resists the change in motion. Connections assembled near Earth would carry this force continuously after decades of aging. A stronger burn could shorten the braking phase, but it would demand more from every support and joint. A weaker burn would protect the structure while requiring an earlier start and a longer period of engine operation. Fuel would control almost every decision. A spacecraft cannot spend all its propellant reaching high speed and still expect to stop. Unless something outside assists it, the ship must preserve enough energy and reaction mass for deceleration, course corrections, and movement within the Alpha Centauri system. The braking reserve might remain untouched for most of the voyage, protected more carefully than almost any other resource on board. A slow leak, discovered halfway between the stars, could reveal that Alpha Centauri remained physically reachable, but impossible to enter safely. Interstellar space could not provide an easy replacement. The gas between stars is far too thin to collect quickly, and no refueling station would exist ahead. Some mission designs would move part of the problem away from the ship. A powerful laser near the solar system could push a reflective sail during departure, allowing a small craft to accelerate without carrying all of its energy source. But the beam would remain behind. No matching laser would be waiting at Alpha Centauri, unless earlier robotic missions had spent years building one. The ship might arrive with less departure fuel, yet it would still need a way to slow. A large sail could attempt to use the light of the destination stars as a brake. As Alpha Centauri grew brighter, photons striking the sail would produce a weak but continuous force against the ship's motion. This might be possible for a very light probe. A human vessel would be vastly heavier, and its sail would need to be enormous, precisely controlled, and intact after decades of dust impacts and radiation. It must reflect nearly all the incoming energy, because absorbing too much light could damage the material. The destination also contains more than one source of light. Alpha Centauri A and B orbit one another, while Proxima Centauri lies far from the pair and shines much more weakly. A sail approaching one star would experience a changing environment shaped by the others, making the final path more complicated than braking toward a single sun. Magnetic systems offer another possibility. A large superconducting loop could create a field that interacts with charged particles in the interstellar medium and the stellar wind. Instead of throwing propellant behind the vessel, the ship would use surrounding plasma as something to push against. The force would be gentle, and the magnetic structure might need to extend across an enormous area. Superconducting equipment would have to remain cold, stable, and unbroken for years. Closer to Alpha Centauri, stronger stellar winds might improve the braking effect. But the winds of 3 stars would not form one simple stream. Long charged wires could be used in a similar way, creating an electric sail that resists the flow of particles. Yet, thin wires would be vulnerable to dust, vibration, and electrical failure. Every approach exchanges one difficulty for another. Engines demand fuel, sails demand area and control. Magnetic systems demand vast fields and long-lived materials. None of them allows the ship to ignore the energy stored in its motion. Gravity could help shape the arrival, though it would not act like a natural brake. A star pulls an approaching spacecraft inward and increases its speed. A carefully planned flyby can change direction, and interactions with moving stars or planets can exchange a small amount of energy. But gravity cannot easily capture a ship arriving far too quickly. At a large fraction of light speed, the vessel would pass through the system before the stars had time to bend its path enough. The faster the crossing, the less useful the destination's gravity becomes. This is the quiet contradiction of interstellar travel. The speed that makes another star reachable also makes that star easier to miss. Even after years of braking, the ship might approach at thousands of kilometers per second. The final reductions in velocity would decide which part of Alpha Centauri it could enter and whether it could remain there. Alpha Centauri is not one compact destination. Alpha Centauri A and B move around a shared center of mass, while Proxima lies so far away that traveling between it and the brighter pair could become another long voyage. The crew could not simply arrive somewhere in the system and choose later. A path toward Proxima might make the 2 sun-like stars difficult to reach. A route toward Alpha Centauri A or B could leave the known planet around Proxima far across the system. Changing that decision after braking could require years and propellant reserved for settlement. Observations made during approach would therefore matter more than plans written near Earth. Telescopes in the solar system might identify planets, dust, flares, and possible resources, but the ship would finally see the system from close range. Hidden worlds could appear. A planet once considered promising might reveal a dangerous atmosphere, extreme radiation, or an orbit unsuitable for a settlement. Another object, ignored from 4 light-years away, might contain water or offer a safer place for construction. The crew would receive this information, while the time for changing course became shorter. Earth could not guide the decision. A discovery transmitted home would take more than 4 years to arrive, and any reply would return after the ship had already committed to its path. The people aboard would choose using their own measurements, their remaining fuel, and the condition of a vessel that had crossed the interstellar void. There might be no ideal option. The safest orbit could be far from useful resources. The most interesting planet could lie near an active star. The easiest destination to reach might not support a permanent human presence. During the final approach, Alpha Centauri would stop looking like one fixed light. Alpha Centauri A might appear warm and sun-like, while Alpha Centauri B shone somewhat dimmer and more orange. Their slow movement around one another would become visible through repeated observations. Proxima would remain a faint red star at a great distance from the pair. The simple name Alpha Centauri would open into 3 separate environments, each with its own gravity, radiation, and possible worlds. Navigation would become more active after decades of apparent stillness. Nearby stars and planets would shift rapidly against the background. Course corrections once planned across years would now matter across weeks or days. The ship would prepare for orbit, a controlled flyby, or a path toward a planet, moon, or construction site. Its forward shield might no longer face the only important direction. Dust and charged particles could arrive from changing angles as the vessel entered the stellar environment. Radiators, antennas, sensors, and habitats would need to reposition. The spacecraft would begin transforming from an interstellar vehicle into something capable of living inside a star system. Parts used during the crossing could be discarded or reused. Empty tanks might become storage. Shield material could become construction stock. The main engines could remain necessary for months while the ship moved toward its selected destination. Crossing the outer environment of Alpha Centauri would still leave enormous distances ahead. Passing near Proxima would not mean reaching the 2 brighter stars. Entering orbit would not mean finding air, water, or a surface where people could safely live. The crew would have crossed 4 light years only to discover another system of journeys waiting inside the destination. Yet one threshold would change everything. Once the ship had slowed enough for the gravity of Alpha Centauri to hold it, the vessel would no longer be passing through by momentum alone. It would belong to the system physically, even before anyone found a world to call home. The stars ahead would stop being lights the ship was chasing. They would become the sources of heat, radiation, and gravity, controlling its future. Behind, the sun would remain a distant point carrying messages from years earlier. Ahead, 3 stars and their uncertain worlds would decide whether the voyage had reached a home or merely another place where survival depended on machinery. And once the ship had finally surrendered enough of its impossible speed to remain inside Alpha Centauri, the destination opened into something more complicated than one nearby star. 3 different suns, moving worlds, and a planet that might be Earth-like only from 4 light-years away. From Earth, Alpha Centauri often appears as one bright point in the southern sky. Distance presses its members together until separate stars become a single light. A ship entering the system would watch that simple image come apart. Alpha Centauri A would be the most familiar. It is close to the sun in size, brightness, and age, shining with a warm light that could make it seem like the natural center of the new system. Yet familiarity from a distance would not make the environment identical to home. Its companion, Alpha Centauri B, would never be absent from the larger sky. The 2 stars orbit a shared center over a period of nearly 80 years, sometimes drawing closer together and sometimes moving much farther apart. From a planet around either star, the other could become an unusually brilliant object, changing position and brightness across decades. A stable orbit could exist around one star, but not at every distance. Farther out, the pull of the companion could disturb a world over time. Any settlement plan would need to understand not only the star it approached, but the slow movement of the binary pair. Alpha Centauri B is slightly smaller, cooler, and dimmer than Alpha Centauri A, though still far more similar to the Sun than Proxima. Its orange light might appear inviting, and observations have suggested that radiation conditions around the 2 bright stars could be less severe than around their distant red companion. A favorable star is only one part of a living world. A planet also needs a suitable orbit, enough mass to hold an atmosphere, a history that preserved water, and a surface where those conditions remain stable. Earth-based observatories could study the system for years before departure, and the ship would improve those observations throughout its approach. Still, small planets close to bright stars are difficult to detect. Some worlds might remain hidden until the vessel was near enough to measure their pull, reflected light, or heat directly. A world around Alpha Centauri A or B might offer a calmer star, but a difficult surface. It could be too hot, too cold, airless, covered in dense gas, or poor in accessible water. Another might provide useful materials without any possibility of outdoor life. Our own solar system contains one inhabited planet, yet the nearby worlds around the same sun are profoundly different. Venus receives familiar sunlight, but hides beneath crushing pressure and extreme heat. Mars lies nearby, but lost most of its atmosphere and surface water. Far from the bright pair, Proxima Centauri would offer a stranger destination. It is the smallest member of the system, a red dwarf with only a fraction of the sun's mass and brightness. Although it is the closest individual star to Earth, it remains separated from Alpha Centauri A and B by an enormous distance. Proxima may take more than 500,000 years to complete one orbit around the other two stars. A spacecraft near the bright pair would not see Proxima hanging beside them like a third sun in one crowded sky. It would appear far away, and traveling from one part of the system to the other could require another substantial voyage. The known world that attracts the most attention orbits the faintest star. Proxima b is at least somewhat more massive than Earth, and completes an orbit in only about 11 days. It circles extremely close to Proxima Centauri, much closer than Mercury circles the Sun. Because the red dwarf is small and cool, that tight orbit places the planet within the region commonly called the habitable zone. A habitable zone describes a range of distances where a planet could, under suitable conditions, maintain liquid water on its surface. It does not reveal whether water is actually present. It does not confirm an atmosphere, oceans, clouds, soil, or life. From 4 light-years away, Proxima b can easily become an imagined second Earth. Artists can place oceans beneath a red sky and show unfamiliar continents around a nearby star. No telescope has yet provided a detailed view of its surface. Its atmosphere, if one exists, remains uncertain. Its history is hidden, and that history may matter more than its current position in the habitable zone. Proxima Centauri is not a quiet star. Red dwarfs can remain magnetically active, releasing powerful flares that send ultraviolet light, X-rays, and energetic particles into surrounding space. Proxima has been observed producing frequent outbursts, including events far more intense than the ordinary sunlight received by Earth. Proxima b orbits so close that those eruptions would reach it with little distance to weaken them. A strong atmosphere and magnetic field could offer protection, but neither is guaranteed. Over billions of years, repeated high-energy radiation may have changed the planet's chemistry or stripped away gases from its upper atmosphere. If much of the air escaped, the surface could be exposed directly to radiation and vacuum-like conditions. The planet might still retain a dense atmosphere created by volcanic activity or inherited during formation. It might contain water beneath ice or underground. A thick atmosphere could move heat around the world and protect the surface more effectively than a thin one. During approach, its telescopes could separate the planet's light from the star more clearly than instruments near Earth. Spectrometers might search for gases in the atmosphere. Changes in brightness could reveal clouds, ice, oceans, or bare rock. Oxygen can be associated with life, but it can also be produced without biology under some conditions. Methane may come from living organisms or from geology. A planet can display an interesting chemical mixture without being inhabited. After generations of travel, the final answer might depend on months of observation, cautious orbital passes, and robotic probes sent ahead of the crew. No one would want to risk the only human population in the system by descending toward a world simply because it looked blue or carried water vapor. Small probes could pass through the upper atmosphere, map radiation, measure winds, and search for landing sites. Others could touch the surface and examine rock, ice, or soil. A lifeless world could be used, altered, and settled according to human needs. A world containing even simple organisms would be scientifically precious and ethically complicated. The crew would have to decide whether survival justified changing an independent biosphere. Proxima b might also be tidally influenced by its close orbit. One side could face the star for long periods, while the opposite side remained in darkness, though the exact rotation would depend on the planet's orbit and internal history. If enough air or ocean existed, winds and currents could transport heat around the planet. Yet this would still be a world without ordinary Earth days. The red star could remain fixed, or move through a limited pattern in the sky. Weather might be driven by a constant difference between the hot and cold hemispheres. Flares would brighten the sky without warning, changing radiation levels across minutes. Living on the surface might require habitats beneath rock, ice, water, or artificial shielding. It could be a tunnel beneath a frozen plain, protected from radiation and connected to machines that extract water, minerals, and atmospheric gases. The ship itself could remain the safest home for years. Its habitats were designed for vacuum, radiation, recycling, and isolation. Moving people onto an unknown world would introduce gravity, dust, weather, chemistry, and possible organisms that the vessel had never faced. Surface dust might be toxic or electrically charged. The atmosphere could react with equipment. Gravity could be stronger than expected for passengers raised in low or artificial gravity. Even if Proxima b had a surface close to Earth's gravity, walking there could require long preparation. Muscles, bones, balance, and circulation would need time to adapt. A planet that looked like home from orbit could feel physically hostile to people who had never lived on one. Alpha Centauri A or B might offer better alternatives. A planet farther from an active red dwarf could receive steadier light and less violent radiation. The binary stars would still influence long-term orbits, but a stable world close enough to one member might enjoy conditions more familiar than those around Proxima. The crew might find only small, airless planets, giant worlds without surfaces, or debris from a history that never produced a stable home. Large moons could contain water. Asteroids could provide metals and construction material. Cold objects far from the stars might hold ice useful for air, fuel, and agriculture. A settlement could begin in orbit, assembled from local resources while the crew studied every major world. The interstellar ship could become the center of a growing network of smaller habitats, mining stations, probes, and power systems. For generations, the travelers had carried everything with them. Arrival would slowly allow them to gather material from outside for the first time. Near Alpha Centauri A, sunlight could support large power collectors. Around B, the available light would be somewhat weaker but still useful. Near Proxima, solar power would be limited by the star's low brightness, even though planets in close orbits receive enough heat for moderate temperatures. The crew would compare not one beautiful world with one terrible world, but several incomplete options. Every location would offer a different balance between immediate survival and long-term possibility. This is where the mission would become more than exploration. These travelers may have nowhere practical to return to. The ship that crossed the darkness would be aging, and the route back to Earth would demand another interstellar journey. Even if the propulsion system survived, the people aboard might no longer have enough fuel, shielding, or supplies for a return. That reality would change the meaning of habitability. A planet does not need forests and breathable air to become valuable. It may only need water that can be processed, rock that can shield habitats, carbon and nitrogen for agriculture, and a stable place where machinery can be maintained. But survival is not the same as home. A settlement buried beneath the surface of Proxima b could last for generations while its inhabitants never feel the open atmosphere. The planet might supply everything necessary without ever becoming familiar. The first people born there could know Earth only as a star near the edge of visibility. If native life existed, their identity would also be shaped by restraint. Some regions could remain untouched. Human biology might be kept separate from alien ecosystems until scientists understood the risks in both directions. A microorganism harmless to one biosphere could damage another, or simply erase evidence of an independent origin of life. If no life existed, the silence would carry a different weight. Proxima b could possess water, clouds, and weather while remaining completely sterile. The crew might find an environment that looked almost alive but had never crossed the boundary into biology. The nearest potentially habitable planet could reveal that suitable temperatures and liquid water are not enough. The search could continue for decades, becoming part of the settlement rather than a question answered on the first day. Ships would move between stars, planets, and resource sites. New habitats would be built. Children would grow up under artificial lights or unfamiliar suns. The original interstellar vessel might be dismantled slowly, its shielding and engines becoming parts of the first permanent structures. They would be residents of Alpha Centauri, even if their true home remained a network of sealed rooms rather than a planet. It would be whether any place in the system could support a human future without requiring the fragile ship to remain alive forever. And once the three stars and the uncertain surface of Proxima b had shown that reaching a habitable zone was not the same as reaching a home, the final choice became whether to build a new world from whatever Alpha Centauri offered, or accept that the journey had ended somewhere humanity was never meant to live. The engines could fall quiet, the ship could settle into a stable orbit, and the stars could stop drifting across the navigation displays. Yet daily life would continue inside the same corridors. Air would still move through filters, water would still pass through recovery systems, crops would still grow beneath artificial light. The first task would not be planting a flag or opening a hatch. It would be making sure that the vessel could remain alive while the system was studied. The people aboard had survived because they trusted slow decisions, repeated measurements, and machines that did not depend on optimism. Robotic scouts could move ahead of the crew, mapping asteroids, moons, planets, radiation belts, and the changing winds of the three stars. Some would search for water and carbon. Others would measure useful metals, stable orbits, and places where large structures could be built without consuming the ship's remaining fuel. Water could become drinking supply, oxygen, radiation shielding, and perhaps fuel. Rock could be processed into walls and protective mass. Metals could replace parts that had been repaired too many times during the crossing. The first cargo taken from Alpha Centauri would not need to be rare or dramatic. Its value would come from the fact that it did not begin the journey inside the ship. The crew would be operating machinery in an unfamiliar system, far from the workshops that built it. Small vehicles would travel away from the main habitat and return carrying material that had never entered a human environment. Dust could damage seals. Unknown chemistry could contaminate equipment. A navigation mistake could leave a crew or robotic craft drifting beyond recovery. The ship's reactors would provide reliable power. Its farms would feed the population. Its medical facilities, workshops, records, and pressure shelters would offer a level of security no new settlement could match immediately. Additional habitats might be assembled nearby using stored modules and local shielding. Tanks emptied during deceleration could become rooms. Sections designed for propulsion might be converted into factories. Sacrificial shield layers scarred by dust could be cut apart and reused. An engine built to cross light years could become a stationary power system. A corridor once connecting fuel systems might become part of a school or medical center. Material chosen for one journey would enter a second life no engineer near Earth had fully planned. Its oldest structures had already survived decades of radiation, vibration, repairs, and thermal stress. Keeping every part active would consume resources better used for the settlement. For people born aboard, the ship was not only a machine, it was the place where families lived, children grew, and generations were remembered. Removing a habitat could feel like demolishing a hometown, even when the material was needed to build a safer one. A cluster of habitats could slowly spread through a stable orbit. Greenhouses would expand. Workshops would become larger. Shielding gathered from local rock could surround living spaces that no longer needed to remain light enough for interstellar acceleration. For the first time, the community could build without asking whether every kilogram had to cross 40 trillion kilometers. Rooms could become wider. Water reserves could grow. Radiation shelters could be buried beneath thick layers of processed stone. Spare parts could exist in quantities impossible during the voyage. The ship's farms had been designed to use limited space, water, light, and nutrients with almost no waste. In Alpha Centauri, larger growing areas could be built, if enough energy and material were available. New crops could be planted. Soil-like systems might replace some hydroponic equipment. Biological diversity could increase, making the food supply more resilient while changing the appearance and smell of human life. Every habitat would remain sealed. Every entrance would lead through pressure doors. The people of Alpha Centauri might build a civilization across planets and asteroids while never experiencing an unprotected outdoor life. They could possess more space than any generation aboard the ship and still remain separated from the surrounding system by walls. Human beings have always lived by adapting environments with tools, clothing, shelter, agriculture, and shared knowledge. Alpha Centauri would extend that dependence until the boundary between technology and nature became impossible to separate. Its air would be made and measured. Its light would be scheduled. Its water would be cleaned and returned. Its safe temperature would exist only because reactors, pumps, and radiators continued working. Resources could arrive from outside, broken structures could be replaced with local material, new habitats could be added rather than fitted into one aging vessel. If Proxima b retained an atmosphere and accessible water, surface spaces might be placed in its safest regions. Thick rock or ice could protect them from stellar flares. Power might come from reactors, geothermal sources, or systems designed to survive the changing output of the red star. A world around Alpha Centauri A or B might offer more stable light, yet reaching it could require years of travel within the system. The settlers would need new spacecraft, designed not for interstellar speed, but for repeated journeys among local destinations. Cargo craft would move water, metal, fuel, equipment, and people. Navigation networks would map the shifting gravity of the binary stars. Refueling sites could appear near useful objects. Communication with Earth would continue through this transformation. The settlers would transmit images of the stars, reports on planets, recordings of construction, and evidence of any life they found. Each message would travel for more than 4 years before reaching the solar system. New inventions might arrive as information and be rebuilt locally. Music and stories could continue crossing the gap. Scientific knowledge could move in both directions, though each exchange would take years. Over generations, the distance could shape language, culture, and identity more deeply than anyone at departure expected. Children born in Alpha Centauri might learn about Earth as the origin of humanity without thinking of it as their personal home. They would know its oceans, forests, cities, and weather through recordings. They might look toward the sun with instruments, identify the point marked on old star maps, and know that every image from there had already spent years traveling toward them. Building another interstellar ship would require enormous resources, reliable propulsion, and a population willing to repeat the crossing. Even if the technology survived, the reason for returning might become less clear with every generation. Its holidays might remember the day the ship crossed the heliopause, the midpoint turn, the first braking burn, or the arrival of local water. Children could grow up hearing the names of passengers who repaired systems generations before Alpha Centauri came into view. New people could be born without reducing the space available to everyone else, provided the settlement could continue expanding. New habitats could carry different designs, communities, and purposes. The voyage would not end with people stepping into a green valley beneath a welcoming sky. It would end with them refusing to disappear in a place that offered no easy home. They would take ice, rock, metal energy, and knowledge, then arrange those things into another small region where human life could continue. If Proxima b contained native life, the settlement might grow while leaving much of the planet untouched. Scientific stations could observe from orbit or from carefully isolated bases. Earth and Alpha Centauri would both receive the discovery years after it was made, and both would have to accept that life had begun independently, beneath two different stars. Every plant, microorganism, and human cell would become part of a new branch of life, separated from Earth by 4 light-years. A greenhouse would no longer be only a source of food, it would be a living environment transported between stars and continued beneath an unfamiliar sun. A child born there would represent a chain of life that began on Earth, crossed the interstellar dark, and survived inside machines until it could grow again from local material. Its deepest danger would be that nothing at the destination promised to justify the cost. Humanity could spend generations crossing the void and find no open world, no breathable air, and no sign that the travelers had chosen the right star. It could become something more difficult, a second place where humanity learned to survive without expecting the universe to be prepared for it. One failed reactor, crop disease, collision, or social conflict could still threaten everything. Local resources would reduce dependence on Earth, but they would not remove dependence on cooperation and reliable machinery. Yet each new habitat, repaired machine, successful harvest, and child born safely would move the settlement farther from the edge of disappearance. Its last active systems could be shut down after the population moved into larger habitats built from Alpha Centauri material. Some sections might remain as a memorial, preserving the rooms where generations lived between the stars. The vessel would become the foundation of the world that replaced it. Only the small lights of habitats, engines, and communication beams would reveal that something had changed. Anyone looking at Alpha Centauri from Earth with unaided eyes would see no city, no ship, and no human history. The light reaching them would have left years earlier. But somewhere inside that point, people could be building rooms, growing food, repairing machines, and looking back toward a sun that had become just another star. The future would belong to the people who continued after arrival, carrying memories of Earth into a time Earth could never observe in the present. Alpha Centauri is close enough to imagine reaching, but far enough that anyone who truly went there would not simply visit another system. They would leave one human world and become responsible for creating another. Long after the engines became silent and the interstellar vessel disappeared into the structures built from it, the journey would continue through every life, trying to make a home beneath those unfamiliar stars. Good night.